Welcome back to the deep dive. Today, we are plunging into some really fascinating research. It gives us this unprecedented look inside how the most advanced AI models actually, well, think. You know, the problem with these amazing large reasoning models, they solve complex stuff, but how they do it, it often feels like a total black box.
Yeah, completely.
So our mission today is to try and crack that open a bit, using insights from a pretty recent academic paper.
Exactly. We're looking at this paper, Topology of Reasoning, Understanding Large Reasoning Models Through Reasoning Graph Properties. Quite a title. It's by Minagishi, Furuta, Kojima, Iwasawa, and Matsuo. And it really does offer a novel way to get at the internal workings.
Right, and the core idea, the big academic leap here, seems to be using graph theory, nodes and edges like mapping networks,
Exactly.
but applying it to the AI's internal computational steps. That feels new.
It is. It's a sophisticated approach. They're essentially building a map, like an internal blueprint, of the AI's reasoning path. The whole goal academically is making this opaque process, AI reasoning, way more interpretable.
Okay, so by the end of this deep dive, hopefully you'll have a clearer picture of this internal topology of AI thinking. You'll get what really separates these advanced reasoners from, say, standard models, and maybe how this deep academic insight could actually help build better AI down the line.
That's the plan.
All right, let's start at the beginning then. They talk about a reasoning graph. What exactly is that in this context, according to the paper?
So, think of it like tracing the AI's internal journey as it solves a problem. The paper defines it as a representation of the model's computational states while it's performing a reasoning task.
Computational states. Okay.
Yeah, and the nodes in this graph, this is a key academic innovation. They aren't just steps in the final output text. They represent these simpler, recurring internal computational states or reasoning steps the model hits.
So states inside the model.
Exactly. They're extracted from the model's hidden states, those complex numerical representations deep inside. So a node might represent, say, the model being in a multiplication state, or maybe even a pause and rethink state, which they labeled something like wait.
So looking beyond just the words it types out, finding these recurring patterns in the machinery.
Precisely. And the edges in the graph, they're just directed lines connecting these nodes. They show the sequence, the path the model takes through these internal states as it works towards an answer. It's mapping the computational flow.
Okay, that sounds, how do you even build that?
Right.
Going from these complex hidden states to a structured graph feels like magic.
Yeah, it's not trivial. The methodology is quite ingenious and really a core part of their academic contribution here. They essentially break down the AI's inference process, maybe segmenting it by new lines and its thinking process output, its scratchpad.
Right.
For each little segment, they grab the model's internal state, the hidden representation from a specific layer. Then, and this is clever, they take all these captured internal states from lots of different segments, different problems, and they use clustering. K means clustering. I think they mentioned K200 as a default.
Clustering the internal state?
Yeah, grouping the similar ones together. Each distinct cluster of similar internal states becomes a node in their graph. They found these clusters often corresponded to recognizable internal activities, like the multiplicative, additive, or wheat examples they show.
Okay. So the nodes are like categories of the AI's internal modes or activities.
Exactly. You could almost think of it as mapping the AI's internal computational vocabulary at this hidden level.
Okay, that makes sense.
And once you have those nodes defined by the clusters, building the edges is straightforward. You just trace the actual sequence of states the model went through for a specific problem, drawing an edge from one node to the next based on which cluster centroid was closest to each step.
So you're reverse engineering its internal path.
Pretty much. Turning that internal train of thought into a visual, analyzable graph. Creating this internal map from hidden states is really a key academic innovation they're bringing.
Right. So, okay, they've built this graph, this internal map. Now what? How does looking at the properties of this, network of nodes and edges actually tell us something concrete about reasoning?
Yeah, good question. This is where the graph theory really comes in, giving that academic insight into the AI's behavior. They analyze the structure of these reasoning graphs using established graph metrics. And what they found is that certain structural properties correlate strongly with advanced reasoning capabilities. They help explain why some models are better.
Okay, what kind of properties are we talking about?
The paper focuses on three main ones. First, cyclicity.
Cycles, like loop.
Exactly. A cycle means revisiting a node you've already visited. Now, in these reasoning graphs, this is super important. It suggests iterative processing, Maybe moments of self-correction or reevaluation, thinking again. They measure this in a couple of ways. The cycle detection ratio, basically. What percentage of problems result in a graph with cycles? And the cycle count, like how many times nodes get revisited on average?
So cycles might be like the AI internally going, hang on, let me double check that step or let me reread that part.
Precisely that kind of internal behavior, yeah. But captured at the level of these hidden computational states, not just the text output.
Got it. What's the second property?
Second is diameter. In graph theory, diameter is the maximum distance, the longest, shortest path between any two nodes in the graph.
Longest, shortest path.
Okay. A larger diameter here suggests that AI is exploring a broader range of internal states, or maybe traversing a wider conceptual space during its reasoning process. More extensive exploration.
Wider exploration. Makes sense. And the third?
Third is small world properties. This is a concept from network science you might have heard of. It describes networks that have lots of local clustering nodes tend to connect to their neighbors' neighbors, but also surprisingly short average path lengths globally.
Right, like the 6 degrees of separation idea.
Kind of like that, yeah. In reasoning graphs, this suggests efficiency. The AI can do dense, focused processing within local groups of related states, but it can also jump quickly between different distant modes of thought or types of computation. It implies a balance between detailed local work and flexible global transitions, maybe faster error recovery.
Okay, so efficient processing, both local and global.
Exactly. They quantify this with something called the Small World Index, usually denoted S, and applying these specific graph metrics, cycles, diameter, Small World Index, to probe the internal dynamics of AI reasoning. That's a really significant part of the paper's academic contribution.
Fascinating stuff. Okay, so they have these metrics. What did they actually find when they compared the graphs from those big, powerful, large reasoning models, LRMs, with graphs from just standard base models? Do they look different inside?
Oh, yeah. Dramatically different. This is really a central finding. Qualitatively, if you just look at the pictures in the paper, like their figure 3, it's striking. The LRMs generate these graphs that are clearly way more complex. You see lots more cycles, evidence of much broader exploration compared to the base model.
And the base model.
Their graphs often look simpler, much more linear, like a straight path with fewer detours or loops.
Okay, so visually different. What about the numbers, the metrics?
The quantitative results really back this up and provide that solid academic evidence. For cyclicity, looking at figures 4 and 5a, the LRMs, they used models like DeepSeek R1 Distill Quinn 32b as a key example, have significantly higher cycle detection ratios and much higher average cycle counts too.
How much higher?
We're talking like an average of around 5 cycles per reasoning sample for the LRMs they tested, compared to basically 0 or very close to 0 for the base model.
5 internal loops or revisits on average per problem. That feels like a fundamentally different way of processing information.
It really underscores how central this iterative revisiting process seems to be for these advanced reasoners. Then, for diameter, they show this in Figure 5b and Appendix E, the LRMs consistently have substantially larger graph diameters. This holds true across different tasks and even different internal layers of the models. It confirms they really are exploring a wider internal landscape.
Bigger exploration space.
Got it.
And small world.
Yep. Small world properties, too, shown in Figure 6. The LRMs demonstrate a much more pronounced small world structure. They have notably higher local clustering, but also longer average path lengths compared to base models, leading to a small world index S that the paper reports is roughly 6 times higher than the base models.
6 times higher S value. Wow. Okay, so it's not just a minor tweak. It's a fundamentally different kind of internal network structure they seem to develop or utilize.
Exactly. These structural differences, more cycles, bigger diameter, strong, small world properties, are strongly correlated with the better reasoning performance of the LRMs. The paper makes a quantitative argument that how these models navigate their internal states, the specific topology of their reasoning graph, is key to their advanced abilities. This is where that academic insight directly connects to the performance we see.
That link between the internal structure and the external performance is really the crux of it, isn't it? Super compelling. Does anything else affect these graphs? Like, does making the problem harder change the structure or the size of the model itself?
Absolutely. They looked into that too, which adds more layers to the academic understanding here. Task difficulty, for instance, clearly affects cyclicity. You can see in Figure 4, the cycle detection ratio climbs quite a bit as the problems get harder, going from simpler math problems like GSM-8K up through Math 500 to the really tough AIM 2024 competition problems.
The harder problems seem to need more. Internal iteration.
That's what it suggests, yeah. More challenging problems seem to push the models towards more iterative cyclic processing. Then there's layer depth.
Inside the model itself.
Right. The properties change depending on which layer you're looking at. Figures 4, 5b, 6b show this. Diameter tends to get bigger and deeper layers. Maybe those layers integrate broader context, leading to wider state exploration.
Interesting.
Cyclicity and the small world index actually dip a bit in the middle layers. The authors guess this might be related to information compression happening there, but it shows complexity across the model's depth.
Okay. And model size. Does bigger always mean more complex graphs?
Generally, yes, up to the scale they tested,
Yeah.
which was up to a 32 billion parameter model. Looking at Figure 7 and Appendix G, larger models tended to show increased cyclicity specifically, higher counts of cycles, and significantly larger diameters. And notably, the 32B model, which got the best accuracy on the AM problems, also had the largest diameter and the highest average cycle count.
That seems kind of intuitive, right? A bigger model has more capacity for complex internal wiring, so to speak.
It does seem intuitive, but there's a really interesting nuance they point out, which is academically important. Check out Figures 7a and 8. While the number of cycles went up with size and accuracy, the proportion of graphs that had any cycles at all, the cycle detection ratio, actually peaked with the 14B model. That 14B model was slightly less accurate than the 32B.
Huh. So more cycles overall in the biggest model, but a higher chance of having cycles in the medium one. Why?
Well, the paper digs into this. They identified that the 14B model sometimes got caught in unproductive loops, showing patterns like language mixing in its output, which correlated with some of these cycles. Basically, not all cycles are created equal. Some were inefficient or even detrimental.
So just having cycles isn't the goal. You need good cycles, beneficial ones.
Precisely. That's a key academic refinement. The quality and the purpose of the cycles seem to matter as much, maybe more, than just having them. This analysis starts to let researchers distinguish between, say, productive reevaluation and just getting stuck in a loop.
Okay, that's a critical distinction. So this detailed understanding of the internal structure, it's powerful academically, but can we actually use this knowledge? Can it help in, practical AI development, like making better training data or designing better models?
Yes, and this is where the research offers a really significant practical innovation stemming directly from their academic work. They specifically looked at supervised fine-tuning, or SFT, a really common technique to boost model performance on specific tasks.
Right, training on good examples.
Exactly. First, they confirmed that just doing SFT tends to increase the reasoning graph diameters. But the really crucial finding came when they compared SFT using different quality data sets. They looked at S1v1.0 versus an improved version, S1v1.1, and another comparison between S1 and Limo. These are detailed in Figure 9 and Appendix J.
And what did they find?
They found that the higher quality datasets, the ones known to produce better performing models after SFT, consistently resulted in reasoning graphs with larger diameters and more cycles.
Wow. So the quality of the fine-tuning data doesn't just affect the final answers, it actually scopes the model's internal reasoning structure, the graph itself.
That's exactly what it suggests, and this is a key practical takeaway. The paper demonstrates that these graph-theoretic metrics, diameter, cycle count, derived from analyzing internal states, can serve as objective, quantifiable indicators of how effective your SFT dataset is at encouraging these beneficial reasoning structures.
So instead of just looking at accuracy scores after training.
Right. You could potentially analyze the internal graphs produced during or after SFT with different data candidates. It gives you a way to measure if the data is inducing the kind of internal